Hello, everyone. Welcome back to the WISER Summer Program 2026. Hope you're all excited for today's session that sits right at the intersection of HPC, quantum computing, and AI applied to a real-world application. We have with us our speaker today, Dr. Seongmin Kim, who is a research scientist in the quantum HPC group at Oak Ridge National Lab, which is one of the premier centers for high-performance computing. His work focuses on integrating quantum computing, machine learning, and HPC to accelerate scientific discovery, developing distributed quantum classical algorithms that bring the power of supercomputing and quantum computing to tackle complex problems across scientific domains. Dr. Kim received his PhD from Pohang University of Science and Technology in South Korea in 2021 and has since held postdoctoral positions at the University of Notre Dame and ORNL before joining as a research scientist in 2023. And in today's session, he will be speaking to us on the integration of quantum computing, artificial intelligence, and high-performance computing for accelerating materials discovery, showing how these three paradigms really kind of come together to tackle one of the most important challenges that we have today in scientific computing. Please join me in welcoming Dr. Seongmin Kim. Over to you, Seongmin.
Yep. Hello, everyone again. Thank you for having me today, and thank you for joining this session. My name is Seongmin Kim, and I'm currently working in the Quantum HPC group at Oak Ridge National Laboratory. Today, I would like to talk about how we can accelerate materials discovery by combining three powerful tools: quantum computing, artificial intelligence, and high-performance computing, or say HPC for short. This talk is not meant to a deep quantum lecture. Instead, I want to give you a broad picture of how these different fields can come together to solve difficult scientific problems, especially in material science. I will also share my own research journey because I think that journey helps explain why this integration is so exciting. So let me start with a brief overview of my research journey. I began my PhD as postdoc in South Korea, where I worked mainly on experimental material science. Then I moved to University of Notre Dame as a postdoc researcher. At Notre Dame, my research focus shifted toward computational material science, especially using machine learning and quantum computing. After that, I joined Oak Ridge National Laboratory, where my work expanded further into the integration of quantum computing, machine learning, and HPC for materials discovery. So overall, my research journey has gradually moved from making materials in the lab to developing computational tools to design them more efficiently. So at postdoc, my research was very experimental. I learned various experimental techniques like wet etching and vapor deposition methods. Using those techniques, I worked on a variety of functional surfaces and material systems, including superhydrophobic materials, superhydrophilic materials, and underwater oleophobic materials, which could be used for solar cell-related films, anti-wearing biotubes, and oil separation filters. These examples from my PhD period represent that early stage of my research identity. So I was learning how structure, chemistry, and processing affect performance. But I was also seeing a major limitation. When I rely mainly on trial and error experimentation, it was really difficult to find the best material due to time-consuming processes. There are just too many combinations of materials, geometries, and fabrication conditions to explore one by one. So one thing that I learned during the period is that materials research can be very creative, but it can also be very slow. You may have a promising idea, but to test that idea, you often need to fabricate samples, characterize them, analyze the results, and then go back and try them again. That process can take a lot of time and resource. So even though experimental science is very powerful, I think I started thinking more seriously about whether we could make this process smarter and more efficient. As I said, trial and error alone is not enough when the problem becomes very complex. Around the same time, AlphaGo really surprised me. It showed us that AI could solve very difficult problems in a smart way. That made me wonder if AI could help with material science, where we deal with very large and complex optimization design spaces. Actually, many researchers are already moving in that direction, using machine learning to predict materials properties and guide design. So this was the moment when I began thinking about moving from mainly experimental trial and error toward computational material science and AI-based design. And at Notre Dame, I worked on combining material science with computational science, especially using machine learning and quantum computing. Machine learning was very useful because it could learn hidden patterns, hidden relations between input features and materials performance. That gave us a very fast and efficient way to make predictions. However, prediction alone was not enough when we wanted to search very large design spaces and find the best structure. So our team also started exploring quantum computing as a possible tool for solving these difficult optimization problems. For example, let us consider a pixelated metamaterials with 50 pixels, where each pixel has two possible choices. In that case, the total number of possible configuration is 2 to the 50th, which is an extremely large number. If we increase the number of pixels only by 1, that is 51 pixel, optimization space, so or say design space size will be twice, 2 to the 51th. This means that optimization space grows exponentially as the number of design variables increases. Because of that, it becomes very, very difficult for classical methods to search the full space efficiently to find the optimal materials. Although machine learning can help by building a good surrogate model that predicts material performance, even with this good predictive model, exploring such a large design space and finding the best solution is still very challenging. This is very hard optimization problems. Actually, this is NP hard optimization. This is where quantum computing becomes interesting because it may help accelerate this optimization button. So to summarize what I have discussed so far, I used machine learning to build a surrogate model for materials design space, and then used quantum computing as a tool to solve the surrogate model. In this sense, machine learning helps us understand and represent our complex design space in a simple form, while quantum computing may help us search that complex design space much more efficiently. These capabilities enabled me to use computational techniques for material science. So at Notre Dame, I started working at the intersection of machine learning, quantum computing, and material science. The goal was not to use quantum computing just because it was a hot topic, but because material design naturally leads to hard optimization problems. And quantum computing could become a very, very useful tool for scientific discovery. So I will explain the details of that idea in the next part of my talk. These are some of the applications we studied in the period at Notre Dame, especially layered and pixelated metamaterials. Metamaterials are engineered structures whose properties come from geometry and arrangement. That makes them especially interesting for inverse design, because small changes in structure can lead to large changes in functional properties. The design space is huge, complex, and non-convex, which is exactly why both AI and quantum optimization can be useful. So this slide shows one example application of our work, transparent radiative cooling, designed with machine learning and quantum computing. The goal was to design optimized layered materials that control light and heat in a selective way. In this case, we wanted to have high transmission in the visible light, low transmission in the UV and NIR light, and strong thermal emission in part of the IR range. This was very useful for energy-saving windows because such a structure can reduce cooling energy consumption in a passive way. But this is also very difficult to design problem. There are many design variables and they interact with each other. So the optimization landscape becomes very, very complicated and large. Here, by using machine learning and quantum computing together, we could design a high-performance transparent radiative cooler. So actually, it was the best performance in the field. So we also tested the design experimentally, which was very important. It showed that this approach, so combining machine learning and quantum computing, could lead to a real material design, not just a computational prediction. More importantly, it suggested that quantum computing could contribute to real scientific research. Since our optimization algorithm was generally usable, we also applied it to other materials design problems, such as photothermovoltaic structures, selective photon emitter, angle-independent optical filters, and optical diodes. These examples showed that combining machine learning and quantum computing can be an effective way to discover high-performance material structures. What I found especially exciting was that these advanced computational tools or not just theoretical ideas. They could actually be used to address real challenges in material science. Because of that, I became more and more interested in building general computational methods for inverse materials design. At that point, I started asking a new question. So, can you make this algorithm work even better for larger and more complex systems? And that question is what I eventually led me to Oak Ridge National Laboratory. At ORNL, the scope of my research became even broader, especially because I had access to powerful supercomputer. ORNL is home to the first exascale supercomputer, which allows me to solve very large scientific problems very efficiently using parallel computing. With that kind of resources, I started bringing together quantum computing, machine learning, and high-performance computing in one research framework. So now, my research is really at the intersection of quantum computing, machine learning, and HPC for material science. The big advantage of ORNL is that it allows me to think not only about algorithmic idea, but also about how to run them at scale on advanced computing systems. That becomes very important when I want to solve very large real scientific optimization problems instead of only studying small example problems. So now I want to step back and explain the basic idea of how material science can be connected to quantum computing. A classical computer uses bits, which are either 0 or 1. In contrast, a quantum computer uses qubits, which can exist in a superposition state of 0 and 1, which is different from a simple 0 or 1. Without going into the details of quantum mechanics, the point for today is that quantum computers process information in a different way from classical computers using quantum gates and quantum states. Because of this, quantum computing may offer advantages for some difficult problems, especially problems related to searching large combinatorial spaces or solving optimization tasks. In materials design, we can often represent a candidate structure as a binary bit string. For example, zeros and ones can indicate the absence or presence of certain material features. As a very simple example, a metal dielectric metal structure could be written as 1, 0, 1. So this is a combinatorial optimization problem, aiming to find the best combination, achieving the target performance or best performance. Each bit string represents one possible material design, and each design has its own performance or energy value. So if we think about all possible binary bit strings, we end up with a very large optimization space. In physics, the term Hamiltonian usually refers to the energy function of a system. In our context, you can think of the Hamiltonian as an energy landscape defined over all possible candidate structures. Every bit string corresponds to one point in that landscape, and the energy tells us how good or bad that design is. Then, the optimization problem becomes simple in concept. We want to find the lowest energy state, which is called ground state. In this setting, the lowest energy state corresponds to the best material design, according to our objective function. Because quantum computing is naturally connected to problems involving energy and ground states, it provides a very useful way to think about minimization problems like this. So this Hamiltonian gives us bridge between materials optimization and the language of quantum computing. There is one limitation. In practice, we do not know the energy of every possible design, or say bit string. Usually, we only have a limited dataset, maybe a few hundred evaluated structures, because securing data point is quite expensive in material science. So what we need is a model that can infer the broader landscape from sparse dataset. So this is where Solvay modeling comes in. We use machine learning to estimate a function that maps material structure like this to predict performance. If the model is good enough, it can serve as an approximate surrogate Hamiltonian over the entire design space. Then we can use quantum computer to solve this Hamiltonian. The one machine learning model we used for this purpose is factorization machine. This is a supervised learning model that is especially useful for quadratic optimization. So it can capture linear terms and pairwise interactions between variables while keeping computational efficiency by factorizing quadratic terms. From the perspective of quantum optimization, this is very useful because the trained model can be written as a form called HUBO, which stands for quadratic unconstrained binary optimization. The trained linear coefficients can be directly mapped to a off-diagonal term, a diagonal term in a HUBO, and quadratic coefficients can be mapped to off-diagonal terms in a HUBO. This HUBO effectively acts as a Hamiltonian that can be handled by quantum computing. So machine learning model does more than just predictive model. It also gives us a quantum compatible optimization form as a surrogate model representing our design optimization space. That means machine learning can bridge the gap between material science and quantum computing. Once we have this surrogate model from factorization machine, we can use it to predict the Hamiltonian value or predicted performance of a certain material structure. This is very powerful because it allows us to repeatedly evaluate many possible designs without running full expensive simulations every time. In other words, the machine learning model becomes a fast approximation of the design space. But prediction alone is not our goal. What we really want is inverse design. Instead of predicting the performance of a given structure, we want to start from a target objective or the best objective and directly find the structure that gives the best performance. That becomes an optimization problem. Once the surrogate model is written as a HUBO Hamiltonian, the task becomes finding its ground state, which means finding the binary vector with the lowest predicted energy of the Hamiltonian. This is where quantum optimization becomes useful in this workflow because it gives us a way to search these large design spaces much more efficiently. So by combining machine learning and quantum computing, we can build a great inverse design model that can explore significantly large optimization spaces. This slide illustrates that not all optimization problems are equally easy to solve. Some HUBOs from toy problems are relatively sparse, meaning only a limited number of variables interact. These toy models are actually quite easier to solve using classical or quantum method. In contrast, there are dense HUBOs, meaning many variables interact with each other. In materials design, especially for large and complex systems, dense problems are very common. And when the problem becomes dense, the optimization usually becomes much harder. That is one reason we are interested in advanced quantum approaches for materials discovery. Okay, to summarize what I have discussed so far, we can use a factorization machine to build a surrogate model that represents the materials design space. And this surrogate can then be solved using quantum computing. However, the quality of the surrogate model is very important. To build a high fidelity surrogate, we need enough data. The problem is that in material science, collecting a large data set is very time consuming and expensive. To mitigate that limitation, we used active learning approach, which combined machine learning, quantum computing, and physics-based simulation in an iterative loop. We began with a small initial data set. For example, 25 or 50 random material structures and their corresponding figure merits from physics simulation. Then we trained the factorization machine on that trained dataset and obtain a HUBO surrogate model. Next, a quantum optimizer predicts a promising material structure based on that HUBO surrogate. But because the surrogate model is trained on limited dataset, its prediction may not be perfectly accurate, especially in the early stage of active learning. So we validate the predictive structure using physics-based accuracy simulation model, which is accurate but expensive. After that, we add the new validated data point back into the dataset, retrain the model, and repeat the cycle. Iteration of these cycles continuously improve the quality of the dataset, which helps machine learning model to make better surrogate models. Then quantum optimizer can do better prediction, eventually identifying a global optimal structure. So this slide shows how active learning works with iterations. Suppose that this is our design space. Actually, real material design space is much more complex than this. When you start from only a small data set, the learned energy landscape may not be accurate. But as we run more iterations and add more validated data points, the surrogate model becomes closer to the true actual design space. And as a result, the model gets better and better. This is why active learning is so important. It improves the surrogate model step by step through a feedback loop without requiring a large amount of training dataset at the start. In this way, active learning let us gradually build a high quality dataset through the repeated machine learning quantum computing process. So from now, I'm going to talk more about quantum computing. So one way to solve the HUBO Hamiltonian, which is surrogate model for our materials optimization space is quantum annealing. Quantum annealing is a specialized type of quantum computing device designed to search for low energy state of an objective function, such as HUBO or Ising model. Compared to universal gate-based quantum computer, this quantum annealing is much more specialized. And that specialization can be a very strength because for certain optimization problems, it can be very effective. In our workflow, the machine learning model first produces the HUBO, and then quantum annealing is used to search for the ground state, which corresponds to the promising material candidate. But one major strength of quantum annealing is that it is designed specially for optimization. Because of that, for now, it can often handle HUBO-type problems much more efficiently than general-purpose gate-based quantum algorithm. It is also relatively straightforward to connect with machine learning-based Seongmin model, since those models can often be written as HUBOs. Another strength is that quantum annealing can be combined very well with classical methods. For example, if the original problem, HUBO problem, is too large, we can decompose it into smaller parts and solve them with quantum annealing and then combine the results. This is often called hybrid quantum annealing, and in practice, it can provide strong performance. Of course, quantum annealing also has some limitations. First, this is not universal quantum computer, so it cannot run arbitrary quantum algorithms. It is mainly useful for specific class of quantum optimization problems. Second, real hardware still has some limitations, such as restricted connectivity, noise, and embedding overhead. That means that the problem we want to solve may not map perfectly or efficiently onto the physical device. Third, for very large or very dense problems, quantum annealing alone is not often enough. So we still need classical support, such as decomposition, pre-processing, and post-processing. Even with these limitations, we found that quantum annealing can be a very powerful tool for solving these HUBO-Seongmin models. And in our work, it showed strong advantages over state-of-the-art classical method, especially when combined with classical decomposition and aggregation methods in a hybrid workflow. Another approach for solving HUBOs is gate-based quantum computing. Gate-based quantum computing has received a lot of attention in these years because it is universal and flexible. In principle, it can be used to run many different kinds of quantum algorithms, not only for optimization, but also for simulation, chemistry, or other applications. Among these methods in this area, the quantum approximate optimization algorithm, or QAOA for short, has become one of the most important approaches. QAOA is a variational algorithm that uses parameterized quantum circuits to approximately solve optimization problems. In simple terms, it tries to prepare a quantum state that gives high probability to the good solutions. So the number of qubits corresponds to the problem size, and it is related to the circuit width. And the number of variational layers and parameters affect how many quantum gates we use. And this is related to circuit depth. From a classical point of view, adding just one more variable, that means increasing problem size only by one, can make problem much harder because the search space grows exponentially. For example, with 10 qubits, that corresponds to 10 qubit problems, we need to consider 2 to the 10th, that is 1024 possible states. If we move to 11 qubit problems, that becomes 2 to the 11th, 2048 possible states. So classically, the cost can grow very quickly as the problem size or circuit width increases. Quantum computing is interesting because, in principle, the quantum system represents these states in a very different way, only using one additional qubits when you increase the problem size by one. That is why quantum computing is considered promising for large optimization problems. However, current quantum hardware is still far from perfect. So we are calling the current quantum hardware is in noise intermediate scale quantum era, NISQ. Gate operations are noisy, and even if the accuracy of single gate seems high, such as around 99.9%, errors can build up when many gates are used in one circuit. So after a large number of gates, because of that, reducing circuit depth is very important on today's quantum hardware. Error mitigation and error correction are very active research topics, but I will not go into those details today. The practical issue is that standard QA can require a large number of gates, even for a HUBO problem with only 30 qubits. So with current quantum hardware, it becomes difficult to solve much larger HUBO problems using standard QA alone. Even though we can simulate quantum states on classical computer, which does not involve any quantum hardware errors or noise, it also has limitations in scaling circuit widths because of the memory limitation on classical computers. So even with noiseless quantum simulator, it is difficult to solve large QUBOs. So now we face an important practical issue. Real materials problems can become very large. For example, QUBOs with sizes in hundreds or even larger. At that scale, directly solving the whole problem on a gate-based quantum algorithm is unrealistic now. That is why we developed distributed QA, DQA. The basic idea is to decompose a large problem into smaller subproblems, solve them in parallel on an HPC-QC integrated system, and aggregate the sub-solutions into a global solution. The global solution is iteratively refined. Then it approaches toward the true optimal solution. This enables us to solve significantly large QUBO problems using current imperfect quantum computing systems. So this is a good message of a broader message from my talk. Quantum computing is more useful when it works together with other computational tools rather than by itself. This slide highlights the performance of the QA. So as I mentioned earlier, standard QA has difficulty in handling QUBOs problems larger than 30 variables because of the current quantum limitations. However, DQA can handle very large QUBO problems like 1,000 QUBO problems. The main point is that quantum computing does not magically solve everything in its own. Rather, by integrating HPC and QC, we can improve both scalability and solution quality. This is what I mean by quantum-centric supercomputing. Quantum resources embedded inside the larger high-performance computing framework. In the sense, DQA not only helps overcome some of the current limitations of quantum computing, but also provides a foundation for taking advantage of future improvements in quantum hardware. Once we have a scalable quantum optimization engine like DQA, we can place it back into the active learning loop here. Instead of using a smaller, limited optimizer, we now use a distributed quantum classical workflow to search for optimal material candidate. This allows us to tackle bigger design spaces and more realistic structures. This workflow enables the exploration of 100-bit system, which is very challenging for standalone gate-based quantum approaches. The main scientific message here is that this kind of workflow can be useful for real materials discovery, not just for abstract optimization problems. For example, when designing energy-related materials, the goal is to find a structure that can reduce energy consumption, improve efficiency, or provide better overall performance under practical conditions. In our case, we already showed that this workflow could design a meaningful structure. The result was especially important because it was not just a theoretical example. The designed structure had real potential for reducing cooling energy consumption in building by passively controlling light and heat. So this tells us that combining machine learning, quantum computing, and HPC can lead to materials design that are not only computationally interesting, but also practically useful. More broadly, this suggests that these integrated computational workflow may become powerful optimization tools for this covering next generation materials. Another important part of this work is acceleration using GPUs. Even though we are discussing quantum algorithm, much of the overall workflow is still classical. By using GPUs, we can speed up these classical parts very significantly. This slide shows that GPU acceleration can greatly improve the performance of DQA by more than 10 times. So again, the key theme is integration. High-performance computing, GPUs, AI, and quantum computing working together in one framework for accelerating large-scale optimization. Now, I want to show a few examples of how this integrated framework can be used for real-world materials design. In this part of work, actually, I used quantum annealing instead of quantum DQA way, but the overall workflow is very similar. One example is high entropy alloys, which are compositionally complex materials made by many interacting elements. Because of the complexity, it is very difficult to optimize them using brute force search. Another challenge is the evaluation step here. In some cases, evaluating only one candidate structure can be very, very expensive, especially if it requires MD simulation, molecular dynamic simulations, or high-cost DFT calculations. To reduce the evaluation cost, we used machine learning potential model to replace expensive simulation step. Because this model has very high fidelity, it can serve as a reliable substitute for the original expensive simulation in this optimization workflow. This example shows an important broader point. These computational ideas are not limited to one specific material system. The same general framework can be applied to different scientific areas. So here is another application direction: radio frequency integrated circuits, RFIC. This new example is important because it reminds us that optimization methods developed in one field can often be repurposed elsewhere. If you have a computational workflow that can effectively navigate large design spaces, it may be useful for not only for thermal materials or alloys, but also for communication devices, photonics, and electronics. That broad range of applications is one reason this research area is so exciting. This slide introduces another method called distributed variational optimization algorithm, or say DVQOA. You can think of this as another framework for solving optimization problems that are relevant to materials design and many other applications. One interesting way to think about it is it has some similarities to neural networks, deep neural networks. In a simple sense, each quantum gate can play a role similar to a neuron. And by stacking multiple variational layers, the model can represent more complex behavior and improve the performance. DVQA is an unsupervised optimization algorithm, and its goal is to minimize the target cost function by tuning the variational parameters in a quantum circuit. A nice feature of this method is that the cost function can come from many different types of problems, such as routing, combinatorial optimization, or materials design. Another important advantage is that this algorithm does not require us to convert the problem into a Hamiltonian form in advance. Instead, it can directly work with the objective function itself. Because of that, DVQA is a very flexible framework and can be applied to a wide range of optimization problems. This slide introduces more challenging problem settings. So far, many of the examples I showed were based on binary design variable, where each variable has only two choices. But in real material design, that is often not enough. Many problems include both discrete choices and continuous parameters at the same time. For example, we may need to decide which materials to place in each layer, which is a discrete choice, while also optimizing the discrete thickness of each layer, which is continuous variables. This makes the optimization much harder because now the design space contains different types of variables together. In other words, we are no longer searching for simple binary combinations, but over a mixed space that is much larger and more complicated. One practical way to handle this is to encode the continuous variables into binary form. By discretizing the continuous variables into a set of binary representations, we can still write the whole problem as a Hamiltonian-based optimization model, like HUBO. Once we do that, the same quantum optimization methods I introduced earlier, like DQA or quantum annealing, can be applied. Then the quantum optimizer gives us a binary solution. And after that, we can decode that binary vector back into the combination of discrete material choice and continuous parameter values. The important point is that this mixed optimization framework is much more realistic for actual material design. And because it includes both structure selection and parameter tuning at the same time, it can often produce better designs than an approach based on binary choices alone. This slide introduces one of our ongoing directions, higher order optimization problems. Up to this point, I have mainly talked about HUBOs, where the objective function only contains quadratic terms, meaning pairwise interactions between only two variables. That is very useful formulation, and many problems can be written that way. However, in realistic scientific problems, interactions are often more complicated than pairwise. In many cases, three or more interactions can interact together at the same time. To describe those systems more naturally, we use a more general form called HUBO, which stands for higher order unconstrained binary optimization. You can think of HUBOs as an extension of HUBO that allow higher order terms beyond the simple binary pairwise interactions. This is important because many real materials and scientific problems are not naturally only pairwise. If we force everything into a quadratic form, we may lose some of the original structure of the problem or need extra transformations that make the problem larger and more complicated. So HUBO gives us a more feasible way to represent the original system, but at the same time, that extra expressiveness makes the problem much harder. The optimization landscape becomes much more logged, which means there are many local minima, and it becomes much easier for an algorithm to get stuck. Also, the quantum circuit needed to represent and solve these higher order interactions become more complex because we have to use much more entangling gates. Because of that, the scaling becomes much worse if we try to solve HUBO problems in a simple, direct way. As the system size grows, both computational cost and the algorithmic complexity increase very quickly. To overcome this limitation, we use high-performance computing together with distributed quantum optimization. Instead of trying to solve the whole problem in one place, we divide the work across many computing resources and coordinate the optimization in a distributed way. By combining HPC and quantum optimization, we can explore this very rugged higher-order energy landscape more efficiently. This allows us to solve larger and more realistic problems than would be possible with a straightforward approach like standard QA. The encouraging result is that this distributed framework can achieve very high accuracy, significantly better than other conventional HUBO servers. So the broader message of this slide is that as our scientific problems becomes more realistic and more complex, we also need more advanced computational frameworks that combine quantum computing with large-scale computational resources. This is one of the more forward-looking parts of the talk. Here, we are exploring whether a GPT-style model can help generate useful quantum circuit automatically. Instead of running a standard variational optimization algorithm loop every time, the idea is to train a model on a collection of good circuits and then use the model to generate the optimized circuits very quickly for new problems. This is exciting because it brings together generative AI and quantum algorithm design. It also shows that AI can be useful not only for materials modeling, like solid modeling, but also for designing quantum circuits themselves. At the same time, this approach still has some limitations. While the quantum optimization step can be accelerated significantly, training the GPT model can be very expensive because it requires collating a large amount of high-quality data set. Another challenge is that different types of problems may require different training datasets. In addition, as the problem size grows, collecting enough training data becomes much more expensive. Although this GPT-based approach is very promising, it is still difficult to apply directly to large, realistic materials optimization problems at the moment. Nevertheless, once the GPT model is trained, the inference step is very fast. So quantum optimization process becomes much faster. Also, because the distributed framework uses fixed size stock problems, this integration works naturally. We do not need to generate circuits for one huge problem all at once. Instead, we repeatedly solve smaller subproblems, which is much more practical for this GPT-based approach. As a result, the overall workflow can solve much larger optimization spaces much faster than standard DQA. As shown here, DQA GPT provides a significant speedup over standard DQA, reaching up to 27 times faster performance. And this advantage is expected to become even greater as the problem size increases. So the main message here is that by combining advanced AI like generative AI, high performance computing, and quantum computing, we can build a much more scalable optimization framework. I think this is a very exciting direction because it suggests a practical way to use AI not only to analyze scientific problems like solid modeling, but also to accelerate quantum algorithms used to solve those optimization problems. So let me briefly talk about one of our future direction, which is how to utilize quantum hardware more effectively for large optimization problems. As I mentioned earlier, one major challenge in quantum optimization is scalability. Large scientific problems are often too big to solve directly on current quantum devices. So our idea is to combine problem decomposition, HPC coordination, and quantum parallelism in a more efficient way. So the idea is that we first decompose a larger optimization problem into smaller subproblems. Then, instead of solving them one by one, we use an cluster these subproblems. The key idea is that if multiple subproblems are independent, we can combine them into a single Hamiltonian and place them on different cubic groups within one large quantum circuit. In other words, one quantum device can address several subproblems at the same time. This is useful because the circuit depths can remain the same as for solving only one subproblem, while circuit width increases. Since circuit depth is more critical limitations than width on current quantum hardware, this could be a practical way to improve quantum utilization. These plots show that as the number of clusters increases, the accuracy can still remain reasonably high. And this enables us to solve large-scale, higher-order optimization problems. So the main message of this future direction is instead of thinking about quantum devices as solving only one subproblem at a time, we want to use them more efficiently by solving multiple subproblems simultaneously within a coordinated HPC QC workflow. We believe this can become an important step toward practical quantum utility for large scientific optimization problems. Lastly, we are also developing an fault-tolerant quantum computing ready optimization workflow. The goal is to connect our distributed quantum algorithm to logical quantum circuits, error-corrected execution, and decoding, so that the same quantum HPC workflow can be evaluated for both near-term and future fault-tolerant quantum devices. Okay, so now let me summarize the main takeaways. First, the integration of quantum computing, machine learning, and HPC is opening new ways to approach materials discovery. Second, machine learning helps us build solid models of complex materials design spaces, while quantum optimization provides new ways to search those complex and large spaces. And HPC makes the overall workflow scalable. Third, the quantum method becomes increasingly useful when applied to larger scientific workflow. That is the central message I hope you take away from this talk. I also want to emphasize one final point. Quantum computing is not only a subject to study on its own now. It can also become a tool for doing science, especially when combined with AI and HPC. That is why I find this field exciting. It is not only about building better computers. It is about using new computing paradigms to help solve meaningful scientific problems. And for its demonstration, interdisciplinary teamworks are necessary. So if you are interested, no matter where you are studying, I think there is a way to build a team for quantum research and for your research domain. So thank you very much for your attention, and I would be happy to take any questions.
Yeah, thank you so much for that, Seongmin. It was a very interesting talk, and we have a ton of questions for you today, but I know you have to leave on time. So I'm gonna just select a few and ask them to you. And okay, the first question is from Vishal from India. What is the current dominant source of error in quantum material simulation, hardware ansatz design, or Hamiltonian mapping, or something else?
So what is the dominant error? Dominant error is from quantum hardware, I think. So if we have deep circuits, quantum errors are accumulated, so final result is very unreliable. So we have to build a short circuit as much as possible. And building a good HUBO Hamiltonian is also very important. That's why we have to collect enough data set to build a reliable surrogate model like HUBO surrogate. Yeah. So building a good data set is very important as well for this workflow.
Thank you. Question from Seongmin. What makes the recognition of the patterns for low data more accurate in quantum computing?
I'm sorry, could you repeat the question?
Yeah, what makes the recognition of the patterns for low data more accurate in quantum computing?
Quantum computing. So most of the part is from classical. So data is purely classical. So we build a HUBO Hamiltonian from classical data to build a HUBO Hamiltonian form. And quantum computer understand this HUBO only. So quantum computer cannot directly interfaces with classical data. And the data set quality can be evaluated by physics model. So maybe we can use any other like finite element method or FDTD or TMM, like optical simulations. So we can evaluate data quality using physics-based simulations, and then we build a HUBO Hamiltonian. Then this quantum computer only understands this HUBO.
Thank you. I guess we have time for one last question, so maybe I'll ask a broader one from Charan. If you were a student starting from scratch today, how would you learn this field? Like, what roadmap would you follow?
That's a great question. So I would recommend using quantum annealing first, because quantum annealing is very easy to use, and there are very good tutorials to learn. And then it's good to learn QAOA, quantum approximate optimization algorithm. So this is the basic algorithm for quantum optimization. So if you have an idea of these two, maybe you can apply your optimization problems for using quantum devices.
Great. Thank you so much.
Thank you for having me today, and thank you for your attention, everyone. Thank you. Enjoy the lectures.
Thank you.
Thank you.
Bye.
All right. Thank you, folks. Have a nice Wednesday.
Thank you.
Bye-bye.